Hello guys, welcome back again to my channel Gamma Digamma. In the last video we did an integral from the MIT Integration Bee 2026 final, and in this video I would like to do a nice double integral again, which has very nice symmetry properties that we exploit to solve it, rather than doing the brute force method. Anyways, let's get started. So in this video, I'm going to write down the integral that we're going to do. So that's I, integral 0 to pi over 4, 0 to pi over 4, arctan of cosine theta cotangent y times secant cube theta tan squared y secant squared y dy d theta, which I will just reorganize nicely. Okay, perfect. So notice there's two integrals, one in y, one in theta, over the same region of integration. The ideal strategy is to, and the obvious one, is to find a substitution that will significantly simplify this junk of an integrand. We have a cosine theta and a cotangent y inside in the arguments, and we have a tangent y, secant, a bunch of secants. There's a cubed in theta and a squared in y. You might notice that the integrand here in the argument of the arctangent function, we have inverse functions rather than the ones that are outside. We have secant instead of a cosine and a cotangent instead of a tangent, and all of these are reciprocals of each other. So the natural substitution one would like to do is r equals secant theta tangent y, not just because we're not doing the substitution just because we notice, but also when we take the differential, and this is a substitution in y. So theta will be treated as a constant. dr is secant theta secant squared y dy. We justify this substitution because we see a secant squared y, and when we think, well, we have to match the antiderivatives as well as much as possible. So we have a secant squared y, and one secant from here will mean we have the bounds of integration. The theta bounds are the same, 0 to pi over 4. But when r equals 0, rather when y equals 0, we have r equals 0. When y equals pi over 4, we will have tangent of pi over 4. R will just be secant theta. So we've managed to produce this nested integral, and we have arctan of 1 over r. You can justify that. You can see that that's true. 1 over secant is cosine. 1 over tan y is cotangent y. Well, and we have used one secant from the secant cube and a secant squared y to form our dr. That means we have one secant, so we have secant taken away from secant cube. We have secant squared theta tangent squared y, which is just r squared. So that's r squared and dr d theta. Notice this substitution was only changing the variable y into this new variable r. The theta was unaffected, and that this is totally fine. The only price we have to pay, if at all, for that kind of substitution is this nested integral, because now the inner integral depends on theta, which is the outer variable. What do we do from now? You might want to feel like, by instinct, perform integration by parts in R. Solve that in terms of theta by plugging in the upper bound, and then integrate for theta. But I haven't tried it myself. I'll tell you one thing, it's gonna be a lot more taxing, a lot more tedious to proceed in with that method. So I propose a way more elegant method. So first let's convert from polar to Cartesian, because now notice we have r and theta, that's akin to a polar coordinate transformation. We want to convert into the Cartesian, and I will justify why we do this later. First of all, the thing to note is r is square root x squared plus y squared, and theta is arctan of y over x. That's the transformation. Our bounds are theta is going from 0 to pi over 4. So let's take the tangent on both sides. So tangent is from 0 to pi over 4, an increasing function. So inequality should be fine. Tangent theta 0 to 1. Now the tangent theta, according to this formula, we can invert that formula, we get tangent theta is just y over x. So we have y over x less than or equal to 1. Now x and y, they're all in the first quadrant because the angle is going from 0 to pi over 4. That's in the first quadrant. The first quadrant is from 0 to pi over 2. Pi over 4 is well within the first quadrant, and x and y are both positive. So we can justify moving the x around on both sides. So we get y is less than or equal to x. Perfect. Let's look at the other inequality, which is r is between 0 and secant theta. Now, secant theta is arctan of y over x, and r is square root x squared plus y squared. We can simplify the secant of arctan using the triangle method of inverse trigonometry. I'm going to skip that. If you have any questions, please let me know in the comments. And we end up with x squared plus y squared over x. And we can square both sides so that we have x squared plus y squared less than or equal to x squared plus y squared over x. And the terms cancel out to basically give us x is between 0 and 1. And that's nice. That's really nice. We have bounds. Y goes from 0 to x goes from 0 to 1. So y is the inner integral. We still have a nested integral. It's in Cartesian as promised. And please bear with me because it may not be evident why this conversion to Cartesian is justified. So we have integral 0 to 1, integral 0 to x. And we have r squared. Now when we change from polar to Cartesian, remember the Jacobi factor, r dr d theta goes to dx dy. So one r is consumed in the Jacobian. One r remains, which will become square root x squared plus y squared. And we still have the arctan of 1 over r. R is square root x squared plus y squared. dy dx. Here the order matters because the nested integral. The region we integrate on, and I can draw a quick diagram, is this line here, which is y equals x. We're just integrating under that line from x equals 0 to x equals 1. So I'm going to shade the area we're integrating on. Now, we can rewrite this integral in terms of x inside and y outside, changing the order of the integration, basically. And let me also change color. That when we do that, 0 to 1, y to 1, you can easily see this by using the diagram, which is again kind of an unnecessary detail right now. Arctan, everything inside stays the same. X squared plus y squared. In this case, it will be dx dy. Now we can easily change y to back to an x because it's a definite integral. 0 to 1, x to 1, and the integrand is also symmetric under such a change, which will really help us and is the first key property of symmetry that we see in this problem. Okay, that's the question. We just interchanged y for x. And now we can add the two i's. So 2i is integral 0 to 1. Well, we have the first integral, which is from 0 to x, added with x to 1. Using linearity of integrals, this becomes integral 0 to 1. So 0 to 1 and 0 to 1, both in x and y. And that's the first real application of exchange symmetry between the integration variables that we are going to see in this video. Now, and here's the next master stroke, is to use the following formula. Integral of 0 to 1 dx over x squared plus a squared is 1 over a arctan of x over a, which means arctan of, sorry, this should be a 1. 1 over a is a times integral 0 to 1 dx over a squared plus x squared. So all we do is use this formula in the case where a is square root of x squared plus y squared, because we already have an arctan in the integrand itself. So when I do that, and we can divide by this factor of 2 that was lingering around, 1/2 integral 0 to 1, 0 to 1, and 0 to 1. We have a times this original factor here, so that will square up x squared plus y squared, the whole squared. Why are we getting a square? Because we got an extra factor of a using this formula. So and that is the same factor as the one we had here, so that squares. And we have 1 over x squared plus y squared plus z squared, where z squared is the new variable of integration that we're introducing from this arctan integral formula. And we will have, now the order doesn't matter, it's 0 to 1. So dx or dy, dx, dz. As brilliant, we can simplify. We get x squared plus y squared over x squared plus y squared plus z squared dy dx dz. Now here's the next master stroke. Cycle the variables, in the sense change x to y, y to z, and z to x. And that we can do because it's all a definite integral. So I is now can be rewritten as y squared plus z squared over, now the denominator is invariant under such permutations, dz dy dx, and cycle once again. So y goes to z, z goes to x. So I is 1/2, 0 to 1, 0 to 1, 0 to 1, 3 integrals on this unit cube, z squared plus x squared over the invariant denominator x squared plus y squared plus z squared dx dz, and this will be a dy. Yes. And then we just add the 3 integrals up. So 3i is 1/2 integral 0 to 1, 0 to 1, 0 to 1 of the 3 integrals we obtained. This first one, the second one, and then this third one. That gives us x squared plus y squared plus z squared plus z squared plus x squared. All of that divided by that invariant denominator x squared plus y squared plus z squared. And the differential elements dx, dy, dz, which we can interchange in ordering. Perfect. Now we see that there's repetitive terms. So we have x squared and x squared. So that's 2x squared, 2y squared, and 2z squared. So that's 2x squared plus y squared plus z squared. All of that divided by x squared plus y squared plus z squared dx dy dz. And a bunch of things will cancel out here. The 2 factor will cancel out. The numerator and denominator will cancel out. So it's just the volume of the unit cube, which is 1, but that's not I. I is 1/3 of that, which is 1/3. And to write everything down finally, integral 0 to pi over 4, 0 to pi over 4 arctan of cosine theta, cotangent y, secant cube theta, tan squared theta, secant squared y. Need some space to write the differentials. Dy d theta is just 1/3. Isn't that a brilliant method of solving this integral? Let me know if you find any other methods of solving this. This, by far, is one of the most elegant methods that I've seen. So thank you for watching this video, guys. Peace out, keep doing math, and like, share, and subscribe to my channel. Send it to your friends if you like it and you want me to grow. Catch you later. See you.